All right, let's go ahead and look at some of the information necessary to complete Lab 14. So the link to this is available in several places, including in the lab assignment itself and on the lab paper. And we have discharge lamps. So discharge tubes are similar devices. Basically, you have a gas that gets excited by a current being passed through, and the elements or the atoms of the element will have electrons jump up to higher states. When they drop back down, they release photons of different energies and different wavelengths that we can see. Um, and well, some wavelengths that we can't see. But anyway, let's look through, tweak some settings on this, and um, see what we can determine. So we can fire electrons one at a time, but that's slow. So we want to go to continuous mode at 24%. So we're going to turn it up one notch. And then for our first voltage, 21.75. So you may notice that when the voltage was a little bit higher, we had something a little bit more exciting going on. But at 21.75, if we check the little graph to the side here, the energy of the incoming electron is actually not high enough to reach the energy of the next excited state of the electrons inside the hydrogen atom. So it stays at level 1, which is called ground state. This happens, like I said, because the individual electrons coming in don't have enough energy on their own to lead to an electron jumping up. Now, we can tweak that a bit. So let's say if we turn the energy back up a tiny bit, go back to 22.5, which is a little bit difficult to dial in. Well, whatever, that's close enough. It's really sensitive, it's hard to dial in. But 23.25, close enough. We have the same effect because we can see the energy level now is above 2, but not high enough to reach any of these other ones. So really, it can be anything in that range. And now the electrons are coming in because they are above that energy for the excited state. Then they're going to knock the electron up to a higher energy level. Then it's going to release a photon when that energy is allowed to drop back down again. These are not a color that we can see, which is why there's kind of like dark things coming off, because these are not going to be in the visible range. Okay, so this time one electron coming in on its own is enough to raise to a particular energy level. Well, let's see what happens if we leave the potential the same. So, again, I think the instructions say 22.5, but this is reasonably close to the same thing. But I'm going to make the electrons come in a lot faster. And there's some certain threshold where now a new electron will hit when this is still in an excited state. And what's happening now is that those energies from the separate electrons are actually combining, and we're jumping up to all of the available states here. So notice some of these are coming off purple and blue, different shades. We might see red. There's some brown compared to the other dark purple. It's another one that we technically can't see. But where's red? Come on. Oh, it's just bad luck. Maybe there was one earlier and I wasn't looking. But red is also a potential option. Okay, but what's happening now is it's jumping up to all of the different excited states, and that's because there's enough energy. Oh, there's a red one, finally. But there's enough energy from these working together that the energies are combining and reaching higher states. Okay, then let's bring this back down. We'll slow it to 24% again, or some suitably small number where you know for sure the electrons are hitting one at a time and the energy is getting released before a new one hits. But this time we're going to take the potential and we're going to raise it up a little bit more, 26.25. So can I go one more? 26. Oh, there we go. 27 is fine. So I want it to, be easier to see on the graph over at the side that we're clearly hitting between energy level 3 is, we can barely read that, and then 4 is covered up. But if you can count, then you know what's next. So the energy of electron coming in is somewhere between 3 and 4, which means it is strictly larger than 2 and strictly larger than 3. And so randomly, this will jump up to either 2 or 3. And depending on which one it hits, determines the color that comes back out when the photon is released. So for individual interactions, it's enough energy to hit multiple different, but not all of the different energy levels of the hydrogen element. Okay, we're going to leave the production rate the same. So we're going to have the electrons coming in at the same rate, but now we're going to maximize the potential. So notice that now the energy is off the charts here. So it's all the way above every different state. Hydrogen might technically be able to get to a 7th excited state, but that would be just a barely above 6. It would still be in this range. But that is not included in the simulation. Okay, but we'll notice that on the side here, it's jumping up to any of these random numbers and then jumping back down to any of these random numbers. And that's because the energy of the individual electrons coming in is enough to reach any of these energy levels. And so it will do so randomly. Sometimes it'll jump to the highest, sometimes it'll start somewhere in the middle. It just kind of depends. All right, and then if we just max out everything, then we get these coming in as fast as possible. We get, again, all the different interactions. Unfortunately, we get fewer of the lower energies just because these are coming in so fast it's pretty much staying high. But this will still technically work. I may turn this down very slightly. And some new colors. I don't think we've seen that color before. All right, that's probably better. I'm going to hold it at 60 just so we can read this a little better. But now we want to turn on the spectrometer. So think spectrometer, basically color meter, or reading the spread of the colors in the spectrum. And we want to let this run for a while. And we're going to eventually see, I'm going to play at different percents here, just so hopefully we can hit different ranges with different frequencies. So notice that I go really high, we see this one a lot. Whereas we get more of a spread of colors if I'm a bit lower. Okay, this is enough though. Again, there are some colors that we can't see. So the ones that are coming off and they're sort of a dark gray purple are the ones that are ultraviolet. It's not something the human eye can detect. And then the ones that are coming off, they're kind of reddish brown, are the ones that are infrared, which again is just something that the human eye can't detect. That's not a color that we can see. Technically, you can look up these wavelengths and find reasonably close values online. We're going to calculate them in a minute, but we want to try to read from these and see where the peaks are. So it's okay if the colors don't look the same to you. I don't always see colors the same way other people do, but we can at least estimate from where the lines are what we think these might be. So here's 400 and 500. We see three different ones. I'm going to pause it just so it lags less. But we see three different stacks of wavelengths between 400 and 500, and then we see one red one out here between 600 and 700. And if we can estimate these numbers, so between 400 and 500, the first line, that's going to be something like maybe 410. So I'm going to write that down before I forget. All right, so it looks like maybe 410 nanometers. And it says down here, this is nanometers, and then 20, 30, midway between 30 and 40. So maybe something like 435 nanometers. Then that would be 500, so that's 490, 480, maybe like 485, because again, it kind of seems like the middle between those lines. And then the final one that's in the visible range of stuff that we can see, let's see, 700, 690, 680, 670, 660, and 650 in the middle of those, so about 655. Okay, then if we look, the low 400s, then kind of the high 400s and the mid 600s, there's a color chart on Blackboard. So the low 400s and mid 400s, that's going to be the blue and violet range. So that matches the colors that are visible here. But again, if you have trouble seeing colors, we can check from the chart. But that's going to be in range here, violet and blue. And then what was the other one? 650-ish. 650. Yeah, that makes sense. So 650 is going to be way out here somewhere. Red is a really wide range. But we see 650 would fall somewhere in here, and that would be red. Okay, so we've got combinations of blue and violet and red for our different wavelengths. And so if we click to view the picture of an actual discharge lamp, so, again, they put a bunch of current through a sample of hydrogen and then use something called the diffraction grating that kind of splits into different colors. And the different ones that we can see here, it's hard to see in the picture, but you've got blue and violet and a little bit of red there. You've got some streaks of other colors that I think are just random light coming in. But if we look at the lamp itself, it's kind of a pinkish purple. Again, I'm not great with colors, but it's pinkish purple, and that makes sense because it's made out of blue and red and purple wavelengths. Okay, then what we want to do now is we want to try to calculate the different wavelengths here based off of the energies on the side. Now, I'm not entirely sure why. Maybe it's just something to do with the waste of energy in the system. I don't know. But the voltages on the battery don't directly correspond to the voltages that we should be calculating by hand. So it doesn't really hurt anything here. It's just a little bit strange. I tried to figure out why and fix that and see if I could adjust the instructions. And we're just going to kind of pretend like it's not a problem because we can still do everything we need to do. So we're going to calculate using the proper numbers, and then we're going to see where that's going to go. So we're going to end up kind of running through these backwards from the way that we wrote them down, but that's okay. All right, then from our formula, our change in energy or energy released is going to come from a constant from our baseline energy, so ground state energy of hydrogen, and then the different levels that these are bouncing up to. And so if you watch carefully when these are going, if you count like what state that it came from and to between these, then we can check these out. So if something drops from third state to second state, because of the way that it's released and the way the numbers work to fix the signs, we subtract in a way what it goes down to, subtract whatever it comes from, and then that's going to give us our energy released. So from this, we'd have 13.6 electron volts, again, which is just a constant. Then 1 over 2 squared means 1 over 4, so that's 0.25. And then 1 over 3 squared means 1 over 9, which is 0.1111, so on repeating. And then if we subtract and take the difference of those, then we're going to take our constant, and then because of the change in levels, we're going to end up multiplying by 0.138888888, and that's going to give us 1.889 electron volts. So, technically 8's on forever, but just a round to match an answer choice. And that's also kind of nice because we can go look, 1.889 is going to be somewhere in the range here, which matches the red, which matches the wavelength that we were looking at. So that's great. So there's the answer to number 13. For number 14, we want to use a special constant to turn this into a wavelength. So we can find the wavelength by taking, it's a combination of Planck's constant and the speed of light, and then convert it into convenient units and slightly rounded, but we get 1240 electron volts times nanometers. If we divide this by the change of energy in electron volts, which we just found, then that's going to cancel electron volts and electron volts. That's going to leave nanometers as an answer. And we get something like 656, which is really close to what we estimated based off of the chart from earlier. Okay, then let's try this for another one. So if we go, again, if we let this run for a while and we see where these are falling and which one release which colors, then we can go and this was between 3 and 2. Then let's do between 4 and 2. Okay, so we would start out the same way, 13.6 electron volts. We're going to have 1 over 2 squared minus 1 over 4 squared. So that's going to turn into 1 over 4, which is 0.25. That's going to turn into 1 over 16, which is 0.0625. And so subtracting those, we're going to have 13.6 electron volts from ground state hydrogen. That's going to be scaled now by 0.1875. So that's going to make this energy release 2.550 electron volts, which we can match to our color chart. So 2.55 is just barely in the blue range, which matches the color here. It's just like kind of like a light blue, sky blue color, baby blue maybe. Okay, but we can find a wavelength from that. We take 1240 electron volts times nanometers, divide by that energy, 2.550 electron volts. So it's going to cancel electron volts and give us nanometers, something like 486. Again, we estimated 485 based off of the chart, and you know this falls in range with the stuff that's on here to just barely be in blue range. So it's great, it's working. For the next one, we would go between 5 and 2. So the change in energy when it drops from 5 to 2. It's going to be the baseline 13.6 multiplied by 1 over 2 squared, because again, that's just where it lands, minus 1 over 5 squared. So this would be 1/4, which is 0.25. This would be 1 over 25, which is 0.04. And that's going to be 13.6 multiplied by 0.21. And that's going to give us 2.856 electron volts, which is early in the violet range. Again, if we check, indigo is like a dark blue, light purple kind of mix, and that seems to match what's here. So that seems good. Let's find this specific wavelength and see how close our 435 estimate was. So our lambda here, 1240 from that special constant. Oops, nanometers, not millimeters. Divided by 2.856 electron volts. So electron volts will cancel. That's going to give us 434 nanometers, which is, you know, pretty close to 435. All right, and then the final one that makes a visible color, and purple here, I guess, is from 6 to 2. So baseline ground state hydrogen multiplied by the scaling factor that we need to find. We're going to start with 1 over 2 squared because that's where it lands, minus the 1 over 6 squared that it came from. So 1 over 2 squared is 1 over 4, which is 0.25, which we've seen several times. Then 1 over 6 squared becomes 1 over 36. And that's going to be 0.027777, so on. Okay, so we've got our baseline ground state hydrogen multiplied by the scaling factor, which is the difference of those, and that's going to make 3.022222 electron volts. If we match that to our color chart, then that's going to be deep purple way out over here because that's almost at the end of our photon energy range. Okay, so again, that makes sense if we look back at our color. Definitely a vibrant purple. Coincidentally, there's one of those directly above it. So where we pause, that was kind of a nice touch there. But then the last one, finding this wavelength. 1240, same constant you should be familiar with by now. Then divide by 3.022222 electron volts, and it's going to make this come out to be, hey, right on the money this time, 410 nanometers. And that is it.